I just got lured into speaking 2 minutes ago. So I don't really want to know what to say, but what I do want to, well, I can't do, but I want to say absolute, all this would not be possible if it wasn't for Ian and Michael and John and who else was there, Ian, all the way in the beginning.
Well, I mean, I organized the first one, and then Michael was a big part of it.
So I think we can just be super, super, super grateful for what these guys have done, because otherwise, we wouldn't have really enjoyed these days, and learning so much, and just networking and learning from each other, and just
stealing shit.
Sharing.
No, stealing shit.
And I think also really important, just seeing how, can I swear?
Yeah, go.
How fucking real this is, and how we are all in the same shit. And that just makes us feel so much better.
Yeah, so I mean, I've always been very passionate and deep about the way things work. I think most of you know that I'm autistic, and my obsession just happens to be bread. Pip, my wife, who is the smartest person I know, says that I try to understand the world through bread. I'll be researching deep biophysical principles of the way life might have emerged, but I relate it to bread. And so this discussion is a part of that ongoing evolution of the things that I'm interested in, and you may not necessarily see how it has a direct application to what we do, and it may have none. It is not necessary to know this, it's just fun to know. So I don't think it's going to make you a better baker, because any craft, it's more important to have person-to-person transmission of knowledge and hands-on doing, fucking up, and just doing it again. So I just want to preface everything that I'm saying, that what I'm sharing is just stuff that I'm really interested in. And it is because often when we take a food, we forget about how it's connected to where it comes from. And I don't mean like, the cow and its story, or the grower and their story. I'm talking about the actual lifestyle of the plant, and why a certain plant made a decision in what genes it decided to express or not express in the seeds that it produces. I'm talking about something much more deep than that, where biology meets physics, where chemistry and all those things combine, and that's really what this talk is about. I've gone out of my way to put together this PowerPoint, and for time purposes, I might rush through some of it, but it will be available both in recording, and I'll upload a PDF version of this for people to follow. In my talks in the past, they've been kind of discursive and rambling. I'm trying to do this very structured because I want people to be able to follow the story that I'm trying to tell. The stuff that I'm really interested in is only at the very end. But I want to share some theoretical foundations for people that may not have a background in some of the basic sciences that inform the discussion. So I'm going to begin by asking a question. How is gluten formed? And this talk is not about gluten. It's not about wheat. It's about all plants that we turn into batters and doughs. And by batter, I mean any kind of batter, not just for bread. So the typical story, this is from modernist cuisine, the guys that are known for the science of bread. It's a terrible book. It gets most things wrong. It has very little understanding. But the typical story is, when hydrated, the gluten and gliadin, the two proteins, bind and form gluten. Glutenin pieces link up via disulfide bonds, a type of covalent bond. The typical story is that gluten and gliadin in water form a gluten network. The water hydrates and swells the proteins. Glutenin and gliadin are attracted to one another. When they physically collide with each other during mixing, they bind and cross-link. The more collisions there are, the more binding, the attractive interactions. Eventually a network develops. The long and short is, gluten forms because of strong attractive bonds. This talk, and this is what this talk is about, gluten forms via phase separation, things going into two separate phases, due to what's called thermodynamic incompatibility. That sounds big, but I'm going to define it here in a few seconds. So just stick with me. If you don't understand everything I'm saying, you will by the end of the talk. Gluten is a general term given to a heterogenous group of insoluble storage proteins from grass seeds. They're something that are in the endosperm and the inside. And in other seeds, sometimes it's put in other parts of the seed, but in most cereals, it's in the endosperm. And it's what the seedling uses for germination as an amino acid or carbon source, an energy source for growth. The insoluble proteins aggregate to minimize their surface area exposed to a poor solvent. Again, if you don't understand, that's okay. Hopefully you'll understand by the end of the talk. And incompatible biopolymer phases. This aggregation occurs spontaneously, like oil and water separating due to entropic forces, i.e., it's the most energetically favorable configuration that it can form. So attractive interactions that contribute to the gel network formation are weak, mostly physical, that means non-covalent in nature and easily broken. So there's a saying in the natural wine world that great wine is made in the vineyard. Has anyone heard that before? So, I mean, there's a lot of non-interventionist, lo-fi wines like pet nats, which are hip now. You know, they're orange wines. And the whole idea that the winemaker doesn't want to do anything in fermentation. It's all about the way it's grown. But what about good bread? Today's talk is about connecting the functional and structural properties of doughs and batters to their raw biological materials. What we observe as bakers originates from the plants we use, where and how they grow, their lifestyle, and all the bits and bobs that make them up. There are many equilibria in food and beverage systems. So it's about how and where things go and in what amount. Distinct phases structure our food and beverage systems, and the equilibria between the phases are changeable. But first, let's define some things. There's going to be a lot of things you may not be familiar with, but I'm going to define it very simply. One of them is thermodynamics. It was invented in the 19th century by three guys. It's just a way of statistically describing the macro properties of something. But in today's talk, it really just means energy or energetics. So when I say the word thermodynamic, or thermodynamically, it just means energetically. That's all you need to know. And when you think of energy, I just want you to think of whether or not something can attract or repulse. That's it. It's very, very simple. So if something is allowed thermodynamically, it means it's more likely to proceed. And if you have a ball at the top of a hill, it's more likely to roll downhill. And if you have a ball at the bottom, it's unlikely to just spontaneously roll up without input force. So this is thermodynamically favorable. It going uphill spontaneously is not. Does everyone understand? Thermodynamic compatibility is when two things can combine, mix, or interact because it's energetically favorable. It refers to interactions between molecules. Molecules are just atoms strung together, and or between molecules and solvent. It's typical of attractive interactions. Thermodynamic incompatibility is when two things do not combine, mix, or interact because it's energetically unfavorable. It's typical or describes repulsive interactions. Too long didn't read. Compatibility means it's attracted. Incompatibility, so everyone gets that? Biopolymer. This is an organic macromolecule. And I'm going to show some photos. Bio just means of relating to life. Poly means many. And it comes from meros. This means parts. So it's something with many parts. There are two main biopolymers I'm going to be talking about today, proteins and polysaccharides. These are the only two you need to know. I think, does everyone here know what a protein is? It's a chain of amino acids that make peptides into polypeptides, which are then, there's two classes. There are those that are metabolic, like enzymes that are responsible for energy production and all that kind of crap. And then there are others that are structural. Those are the two main types. And polysaccharides are just sugar that's put into repeating chains. Sometimes it's branched, sometimes it's not. And proteins and polysaccharides are responsible for the functional properties of all foods. All foods. That's where it comes from. Those are the two main structural agents that foods are structured from, including beverages. Beer, wine, coffee. Like, this applies to every single food you consume. And so I have some examples of some proteins and polysaccharides in cereals. What is a solvent? A solvent is anything that solvates a solute to create a solution. I fucking hate that because it's just circular. So a solvent is the most abundant substance, like an atom, an ion, or molecule that's in a system that can dissolve something. Dissolving just means attractive interactions that occur spontaneously. They require no energy. You put salt into water, sugar into water, it dissolves. And then it results in a homogeneous distribution of interacting substances. There's a saying that like dissolves like. That just means polar. Polar things are able to dissolve other polar things. A solvent can be anything. It can be a liquid, a solid, or a gas. It just means the thing that's most abundant, that's capable of attractive interactions with other things around. So, this is versus insoluble, when things don't mix or attractively interact. And when that happens, they float to the top or they sink to the bottom of the solvent unless they're stabilized by chemical reactions or a network. Solvent properties are changeable. Pure water is its own unique solvent. When I add 10% sucrose to water, it becomes a different solvent. They have different properties. If I add 11% sugar to a water solution, it becomes its own unique solvent. So they're not the same. And so whenever you have a small soluble substance, and there's a lot of them in doughs and batters, it will change the nature of the water and the way the water interacts with proteins and polysaccharides. I just want everyone to understand that. So, whenever other solutes, dissolvable substances are added, the characteristics, like the chemical composition, the pH, the chemical potential, average molecular weight of the solution is shifted. Two unique solvents may wet or attractively interact or not wet the very same surface types. So here's some examples. When you combine gelatin and water and you form a gel in the presence of an oil or air, that gel cannot be wetted by water. And in fact, it becomes more unwettable than the most unwettable or hydrophobic surfaces that are known in nature, which is weird. No one knows why this happens. So it's more hydrophobic than paraffin wax, fats, or silicons. But when you add casein, which is a milk protein, to the same thing, it becomes more and casein itself is more hydrophobic than gelatin. But when you add it to the gel from above, suddenly it becomes wettable again by water. When you add pectin's hydrophilic, absorbs a lot of water. The casein gelatin gel then becomes hydrophobic again. Solution properties change. So example 2, gliadin is one of the storage proteins that's found in most triticea grains. It's one of the gluten forming. It's not soluble in molten sucrose, meaning liquid sugar, which can be a solvent, right? I want you to remember, everything can be a solvent. Gliadin is soluble, so it's also not soluble in water. But when you combine a 50-50 combo of both sugar and water, suddenly gliadin becomes soluble. But if you have a sugar solution less than 30%, it's not soluble in it. So, phase separation. This dude, Biorank, he was the first person to discover viruses. He founded the entire field of virology. He invented enrichment culture, the idea of having a special artificial media in order to isolate a particular microbe. And he was a botanist, and he discovered phase separation due to thermodynamic incompatibility of biopolymers. So when he was developing an enrichment culture using pre-cooked starch and gelatin, he noticed that a drop-like separation occurred of two different aqueous solutions. You had like one and then little dots of another throughout. He investigated the phase separation parameters by altering the ratio and percentage of gelatin to starch. He discovered that distinct phases formed at amounts greater than 0.1%. He used iodine, which selectively stained starch. He discovered the biopolymers, the proteins and polysaccharides in this case, the pre-cooked starch and gelatin, separated into nearly pure phases of starch and gelatin. So you had one liquid solution that contained all gelatin, and the other one that contained all the pre-cooked starch. And one formed little droplets inside the other. One phase formed stable liquid droplets that were dispersed inside another. The second phase was the continuous medium in which the droplets were dispersed. By adjusting the relative concentrations of each, he could control which phases the biopolymers ended up in. So you can see here, when you have more gelatin, the gelatin forms the light phase, and the dark dots are maltodextrin. And in a certain ratio, there's equal amounts of the two phases. And then if you add more maltodextrin, it suddenly becomes the continuous phase, and the gelatin becomes... That's interesting, isn't it? So what the fuck is a biopolymer? Biopolymer, imagine a chain of smaller bits that make like a pearl necklace. After biopolymers are synthesized, remember they're synthesized in the presence of water, they spontaneously fold into small shapes. They shrink up. And that's for thermodynamic reasons. They want to minimize their surface free energy and maximize their entropy. You don't need to understand, just know that after like an organism synthesizes it, like shits out that pearl chain contracts up spontaneously. When you add water to a folded biopolymer, its wettable surface site, so most biopolymers are, a lot of them contain both positive and negative charges. So some of the sites on the biopolymer can interact with water, other cannot. So this is really important to know. There are what are called polyelectrolytes. And this is why it becomes so complicated, because if you change the nature of the solvent, what the polymer does will change, because it will have different charges depending upon the nature of the solution that it's in. So when you add water to a biopolymer, its wettable surface sites hydrate, causing the chain to move more, and then it slowly unfolds. As they unfold, their surface area increases, exposing more wettable surface sites. And then there's repulsive interactions between the polymer and its own segments, because there might be two charges that cause it to repel even more, like opposite charges of magnets. Is everyone understand that? So solvent space in and around a biopolymer chain is inaccessible to other biopolymers due to repulsive interactions. The volume occupied by a biopolymer excludes other polymer chains from that space. So something called excluded volume. If I'm standing here, I'm excluding someone from being in this space. And if you notice, a biopolymer is a chain, like follow the chain. And I want you to imagine drawing a circle around it, or a sphere actually in this case, because they're wiggling around in space in 3 dimensions. The more biopolymers expand, the more volume they occupy. So imagine this as like a basketball or a ball, and inside you have this unfolded necklace or string. All of the water within that sphere cannot be used or entered by other biopolymers, because it's just a general fact, because the biopolymer has a certain degree of freedom, and it prevents other ones from occupying that space. So the more they unfold, the more space that they take up in a solvent. Is everyone understanding everything so far? So, yep, imagine you have two biopolymers A and B. The closest that two compatible, meaning attractive chains can get to one another, is the sum of their radii. So if you draw a circle, this plus this is the closest that they can get. That means that the excluded volume of a biopolymer is 8 times greater than the volume of the biopolymer itself, just based on simple geometry. If polymers A and B are incompatible, they exert a force that repels each other. This is why two macromolecules will not combine. You can read it later. Just know that it's difference between either their affinity for the solvent, like if one likes the solvent better, then it's going to repel the other, or if it's because differences in the chain length or stiffness. And I kind of explain why, but so something happens when you increase polymer concentration. Going from left to right, in a dilute amount, the polymers are kinetically independent. They're not interacting. There's a lot of space between them. But as concentrations increase, the physical actions between unlike polymers are unavoidable, because it becomes crowded in the solution space. Like polymers will then aggregate with unlike polymers. And when you reach this concentrated critical concentration, you get phase separation. The incompatible biopolymers separate into 2 distinct liquid phases called the water and water emulsion, where you used to oil and water, or the reverse of that, which is a water and oil. But there's something called a water and water emulsion, and it was discovered by. So what happens is you have polymer A, biopolymer B. You add them to water. When they mix, they form what I just showed you. The entropic forces acting on biopolymers at and above the critical concentration is so that the forces acting upon them, this is the critical concentration here, the forces acting upon them, and this represents osmotic pressure, is so great that it rises by orders of magnitude. This is orders of magnitude. So it becomes energetically more favorable for the incompatible biopolymers to spontaneously separate into their own phases. This is Vladimir Tolstoy-Guzov, not actually him. And if anyone can name the movie this was taken from, I would. But he was a Russian. He originally trained, and his team. But anyway, I mean, he's important, and he's really what his work led to a huge breakthrough. Over 4 decades of experiments, they discovered that thermodynamic incompatibility of food biopolymers is the rule, not the exception, and that the critical concentration for phase separation is already naturally present in most food and beverage systems. They show that the incompatibility is general in nature, and it occurs between the following classes of biopolymers, so all proteins and polysaccharides. Structurally dissimilar polysaccharides, so branched versus linear. Between proteins belonging to different solubility classes, between proteins differing in conformation, their molecular shape, and between native and denatured forms of the same protein or aggregated, unaggregated forms of the same protein. In short, like goes with like. Is everyone following so far? Good. So phase separation threshold of different biopolymer mixtures occurs in these amounts. So for polysaccharides are stiff, so they don't move around a lot. So when they float, they tend to have very little amounts. Even at 1% or 0.1%, a polysaccharide can cause phase separation. If you notice for unfolded proteins and polysaccharides, the concentration, the critical concentration at which phase separation occurs is slightly higher. At 2 to 4%, globular proteins and polysaccharides, globular proteins are just kind of spheres. And those tend to be enzymes, most things that are soluble. It's slightly higher. And so if you notice, number 2 is similar to wheat dough systems, meaning unfolded proteins. So that's typical of casein, gelatin, gluten. So phase separation changes the concentration and distribution of water in biopolymers. So water is not distributed evenly between the phases. The moisture content of each phase varies between 30 and 90%. That's by the total weight of the phase. So 100% of the phase, it can be 30% is water and 70% is solids. So if I translate that to hydration for bakers, the 2 different phases, one could be 43% hydration, the other could be up to 900. So water is not evenly dispersed. I want everyone to really understand that. Phase separation increases the concentration of biopolymers relative to their initial solution. So imagine that you have initial solution that contains 1% polysaccharides and 10% protein. After phase separation, like you can see here, the concentrated phase might have 10% protein relative to water, and it's its own phase, and the other one will have, 20% polysaccharides, or it goes from 1 to 10 to 20 and 50. It changes the water distribution, but also changes the concentration of the polysaccharides within each phase. Does everyone understand that? No. Okay, so let's say in wheat flours are 1% pentosan, typically for refined wheat flour, and 1 to 2%. And let's say they're 10 to 12% protein. You add water, they're going to separate into different phases. And what happens is it goes from being 10% protein in the total mixture, if they didn't phase separate. In the separate phases, that protein goes up from 12 to maybe 20, 30% in its own phase, the concentration of it. Huh? Because of differences in water. Remember, because we said before that the hydration between the 2 different phases can vary as much from 43% hydration all the way up to 900. Water is not evenly distributed between the phases. Phase separation characteristics determine water distribution, and this is changeable. This is all going to be online if this is boring you. But interactions between biopolymers can be modulated due to changes in the following things. The ionic strength, which means the presence of salts or other charged solutes, by changing the pH, by biopolymer type, the solvent characteristics, or most importantly for us, mixing composition. That means we can add certain ingredients and it changes the phase separation characteristics, how and where water goes, how and where the biopolymers go. And most of these interactions are physical, not chemical. Food structures are unpredictable. They're heterogenous, heterophase, multi-component systems. What that means is that a food can be a gel, emulsion, suspension, and foam at the same time. So examples are bread and ice cream. They're all of those at the same time. Suspension just means solid particles are suspended. They can have one or more continuous phases. They can contain multiple dispersed phases, that can be either gas, liquid, or solid simultaneously. You can have gas bubbles, like air bubbles. You can have liquid phases. You can have solid that are suspended. And what's more, the dispersed phases, the little droplets, they themselves can contain dispersed phases. I've seen papers where people have created water in water in water in water emulsions. And they're primarily governed by physical interactions of proteins, polysaccharides, and the solvent. So how does water interact with other molecules? Through hydrogen bonding. It's best to think of hydrogen bonds as short, attractive interactions rather than bonds, because, number one, water molecules are always moving. Number two, the attractive interactions are really fucking weak. The strength of the water molecule's motion above, like any temperature above 0 degrees, which is the freezing point of water, the molecules are moving about. And the strength of that movement is greater than the strength of a hydrogen bond. So that means that when a hydrogen bond forms, it just breaks again. So they don't last very long. They're extremely short. A hydrogen bond typically only lasts between 1/trillionth to 1/billionth of a second. So when you think of water being bound, no water molecule is ever bound. It just forms a short, attractive interaction with something. Hydrogen bonds are unstable and extremely short-lived due to these weak interactions. So why the fuck do food scientists distinguish between bound and unbound water? The short answer is because it's not a real fucking science, in my opinion. Mostly, food science is like the community college of sciences. There's an American comedian that calls community colleges as high school with ashtrays. And because food science is primarily concerned with engineering and compliance rather than actually understanding the way things work. So that what that means is that water activity, the idea of water activity within something is stupid. It's a flawed concept. Because no water can be permanently bound somewhere. So a good example, it's like me saying that the average value of the average Tasmanian value of the Australian population is 2.1%. That's a meaningless thing to say, because 99.9% of all Tasmanians are distributed within Tasmania. So water activity would be a measure of all of the Australian population, but it doesn't tell you about where the Tasmanians are distributed within that population. So how does water stay inside food and biological systems? Well, it's not held in place by binding, it's held in place by forces that arise due to pressure differentials. Porous material, like sponges or any dry particulate matter, meaning small particles, they have tiny nooks, pores, and crannies. So you can see these pores formed within, but they also have little pores and cracks and crannies within the physical particles that make up the whatever. The wettable surfaces, the ones capable of attractive interactions of particles and other physical material in the media, create a net positive attractive force, or a negative pressure that pulls the water towards it, just like sucking through a straw. The greater the wettable surface area, the greater the force of attraction. Water transport in plants occurs through similar phenomenon. So here, because this has more exposed surface area, in the capillary is small, it creates negative pressure, it can go up further than here. Water is distributed differently. And everyone kind of intuitively understands that, right? And what that means is that mini equilibria are possible. So water transport in plants. You have water, it sucks it up due to the exact same principle that I just explained. So how is water moved in plants? Via pressure gradients. There's different kinds. There's capillary, osmotic, hydraulic, but they all work according to the principles that I just showed you. So water leaves the system through evaporation. It exits via small pores in photosynthetic tissue. Photo is any green tissue that's capable of photosynthesis. Through little openings called stomatal openings. And the stomata can be selectively opened and closed. It's like a little hatch. It occurs in leaves and in green seeds. So there's little pores in the seed that allows water, like a little vent that it can open and close. And so seed feeling. You have all of these nutrients, and they're brought in. The monomer nutrients, so the constituent things that make up the bigger biopolymers and the things that we need for nutrition. They're brought in from soil or sugars produced from photosynthesis in photosynthetic tissues and organs. And it goes from here, it's transported along with the water eventually up to the seed. And once it's at the seed, these small little bits are then made into biopolymers. And there are three main biopolymer types within a seed that are used for storage material: lipids, polysaccharides, and proteins. People, whenever they talk about yeast and bacteria, they talk about glycolysis and they talk about sugar. They only focus on sugar. Sugar, sugar, sugar. That's what fuels metabolism. That's what causes cells to have energy. It's what causes them to go. But the thing is, it's not the sugar, it's the carbon. So glycolysis often is you can have something that's carbon-based. You can have a biopolymer that has carbon in it, and it will break down that biopolymer and pass the carbon along until it gets to whatever. That means that lipids, polysaccharides, and proteins can all be used as an energy source. It's the basis of the keto diet. Like, don't think about just sugar, think in terms of carbon. Carbon is what causes energy creation in cells, and all three of those can be a source of energy in a plant. So they store them within the seed as storage reserves for nutrients for the seedling as it germinates. So the wettable surfaces of small ions and molecules inside the seed help pull the water into the seed interior. So water is being shipped up via the negative pressure potential, and there's a seed, and the water is coming up, and then within the interior, where these storage biopolymers are being constructed, So you have the evaporation pulls it up, and then water's pulled into the seed interior by the greater surface area of all the small things that have been exported. So the small monomer constituents that are used to make the longer biopolymers cause the water to move into the seed interior, where the storage compounds are going to be eventually deposited. As the grain matures, the little things are then made into bigger things, right? So you go from sugar to starch. You go from amino acid to eventual storage protein. Does you want to understand that? And what that means, when they're polymerized, they fold up. I talked about that earlier. And that means that they expel their water, and they become hydrophobic because it wants to increase the stability of that biopolymer in its storage state. If it were unfolded, that means that it would then biochemically react with something, and then it wouldn't be available. The seed needs to store it, lock it away for future use by making it stable. So it decreases the wettable surface area within the seed. So at physiological maturity, the seed finishes building all the high molecular weight storage compounds. Physiological maturity equals the equilibrium moisture content of the seed. It corresponds to the maximal wettable surface area that will remain within the seed indefinitely, i.e., the inside of the seed cannot hold any more moisture than it does during physiological maturity. That's because all the small things had a lot of surface area. They're made into big things, and they have less surface area. And once the seed is done making all those long biopolymers, that represents the equilibrium. They can't hold any more water. And the seed needs to become stable for storage in the ground. So it opens up its own little stomata, and it releases excess moisture. And during that process, the seed will go from whatever its equilibrium moisture content is down to 14% moisture. But what this means is that the moisture content of the seed at physiological maturity should correspond to the optimal hydration of milled flour from the seed interior. Does it? Fuck, yeah. as far as I'm aware, I'm the first person to discover this principle. I realized that it was thermodynamic in nature, and so most studies report that the wheat kernel moisture water content at physiological maturity ranges between 33 and 41%, which corresponds between 49.25 and 69% hydration. And when you find studies where they take weak wheats, which are on the lower end of that, their optimal hydration, according to, there's a test that you can do. You don't need to understand what that test is, but the moisture content at physiological maturity corresponds exactly 1-to-1 of the optimal hydration of that wheat. This applies to all flours. So lifestyle determines the storage seed polymers. Cereals predominantly synthesize starch, and that's because it's the cheapest, easiest, fastest storage biopolymer to build. And the amount produced is based upon photosynthesis and sunlight. So sunlight's cheap and abundant. Legumes synthesize higher amounts of protein, and that's because of their role in the biological fixation of nitrogen. Nitrogen is one of the main sources of protein. So you can see over here, this is the carbohydrate percentage. These are cereal seeds. They're really high in carbohydrates. Here you have legumes. They're really high in protein content. And then you have other things like oil seeds and tree seeds. So oil seeds and tree seeds synthesize fat as their primary storage compound. Lipids are the most energy-dense biopolymer. They have twice as much energy per gram as polysaccharides, and lipid content in seeds increases with plant woodiness and shade tolerance. That means that woody shrubby plants grow in denser, more crowded, shaded conditions. It means that there's more competition and less nutrients. So they're going to try to maximize the amount of energy that they can store in the seed. So seedlings, therefore, require a greater amount of stored energy during germination due to that greater competition and lower nutrient availability. So there's been a lot of studies that began in the 1930s, and there's about 24 of them, where you make a dough, and then you centrifuge it. You put it in a little test tube, and then you spin it at 100,000 G for at least 1 hour, and it phase separates into different fractions. And they've studied this in bread batters, bread doughs, wheat, rye, oat, triticale, spelt doughs, batters, pancakes, crepes, cake batters. I've looked at all of them. And they've shown us that phase separation, so when you centrifuge it like that, two things to note. Once you go above 100,000 G, it doesn't have any greater extraction. You can go all the way up to 300,000 G and you'll get the same results. It separates into these fractions that are based upon density, going from lightest all the way down to heaviest. And this is what a dough is composed of. If you remember the little droplets that I showed you earlier, there's a continuous phase, which makes up the medium, in which all these other things are dispersed. And these are the separate phases. So each phase has it's a pure phase of biopolymers and water. And it might have other constituents. So this is what a dough actually looks like. You just recombine it, it's going to be these little droplets with a continuous phase. So this is the way a dough is structured. So this is a wheat dough that's been fractionated. And this is, as you increase water within the dough, you get greater fractionation. But once you get to a certain hydration, you're able to separate it into 4 basic phases. The first one is the dough liquor. That's just what it's called. So you're going to hear me talk about it as the dough liquor, the aqueous phase. And it contains most of the soluble things. All the soluble things go to this phase. This phase has the most amount of water, meaning it's the least dense, and it contains everything, this is where the microbes live. And it contains all the sugar, salts, minerals, all that list, all the things that are eaten, all the things that affect dough's property, all the small molecules end up there. Next you have the pentosand gel. So the aqueous phase, here's the amount of dough weight, and here's the percentage of water. And as it goes down, you can see that the water percentage of each phase decreases. Starch is its own phase, it's 30% water. This is what each phase contains. The doughs at the left, you can see that it's the moisture content. Moisture means of the total weight of the dough, but it's not hydration. So meaning if you have 100% dough, a kilogram of dough, if it's 40% moisture, that means it's 600 grams of dry material and 40. So I've converted it to hydrations down here of what the hydrations correspond to. The hydration of wheat flour components. This is how much water these wheat dough fractions can absorb when they're on their own, when you isolate them and you add water to it. So if you notice, they absorb less water in real dough systems. So on your right, you can see, so hydrated biopolymers contain less water than in real doughs when tested in isolation. Answer, why? Well, it's because of changes in the solvent characteristic. So in the aqueous phase, all the dissolved things like the salts, sugars, amino acids, fats all end up in the aqueous phase, the dough liquor. And that changes the nature of the solvent, and that then changes the way the other phases interact with each other. And so there's an equilibrium pressure that develops between the separated phases that pushes back on them due to phase separation, and it prevents further absorption. So, you know, hypothetically, gluten should hold twice its weight in water, but it doesn't in real-world doughs. So we think of microbes living in dough systems like this, when in reality, they really live like this. The brightly colored bits are the microbes. On your left is E. coli, and on the right is yeast. These are just model systems. This is a phase-separated system that's using gelatin and dextrin. And remember, these are aqueous phases. It's a water and water emulsion. The microbes prefer to live in the dispersed aqueous phase. Dough liquor, it's where all the cool microbes hang out. As hydration increases, so too does the total volume of the aqueous phase. So just to go back, this phase at the top, the aqueous phase, contains all the lipids. It contains all of this stuff, what they eat. It also produces all the shit that they shit out. All the acids, ethanols, organic acid, everything ends up there. If you look, it represents 5 to 20% of the dough weight. I just want you to remember that. It's the phase at the top. It's dispersed as little droplets. These little droplets. As you increase the dough's hydration, this is hydration here, the amount of the aqueous phase increases. And what that means is that as a dough's hydration increases, the size of the dispersed droplets increases. Does everyone understand that? So the aqueous phase, the amount of solids that's in it and the amount of nutrients and its viscosity remains the same. So as soon as the aqueous phase arises and you have little droplets, it's typically... So what does this mean? This means that when you increase hydration, bigger droplets can support larger cell populations within them. Does everyone kind of understand that? Wetter doughs don't ferment faster kinetically. It's not due to rate. At hydrations above 49%, when a separate aqueous phase, that's the hydration at which a separate aqueous phase appears. The diffusion and the percentage of nutrients within the aqueous phase remains the same. So if you have a dough that's 50% water or a dough that's 90% water, the amount of the aqueous phase increases, but the amount of nutrients within the aqueous phase remains the same. Let's say it's 5%. As soon as the little bubbles appear, it's 5% nutrients when it's only 1% aqueous phase. When you go up to 90% dough, the droplets get bigger, but it's still only 5% nutrients. That remains stable. Does everyone understand that? Great. Wetter doughs ferment faster because they support larger total populations within their dispersed droplets. Small droplet size also explains buffering capacity of stiffer doughs. That means that it changes how much acid is produced. And that's because smaller droplets have greater surface area relative to their volume, and the things that can absorb acids are proteins. And everyone's with me, I hope. So we can identify 5 main hydration zones for all batters and doughs. Some of these apply only to wheat, some apply to gluten-free. And you can see they're related to the seed properties. So it's 33% hydration, 45, this is relative to whatever. At 30 to 33% hydration, which corresponds to most extruded pasta, it's the emergence of water not absorbed or adsorbed within the biopolymer capillaries, pores, network, or interior, corresponds to the emergence of electrical conductivity. So below that, if you fucking try to measure it doesn't conduct electricity within it, but it corresponds to the lowest hydration at which you can form a dough. It corresponds to the first hydration at which you have limited microbial growth and limited enzymatic activity. At this hydration, you begin, below this hydration, the aqueous phase is embedded within and the starch is embedded within the protein network tightly. And it then therefore limits the diffusion within the aqueous phase. All these things decrease microbial growth and enzymatic activity, but above 48%. So if you notice, it kind of corresponds to the hydration that Lievito Madre, or whatever you guys talk about, like the starters that are maintained for panettone correspond usually to these or below this, because it really limits microbial growth. It's related to the thermodynamic properties of the seed and what the seed produces. This hydration corresponds to everything I talked about before, to the equilibrium moisture content of the seed at physiological maturity. It corresponds to the separate, so whatever the equilibrium moisture content of the seed is at physiological maturity will then correspond to these other two things, which is optimal absorption and to when a separate aqueous phase becomes present. And at this hydration range, this really only applies to wheat and spelt. This is the hydration at which peak phase separation of biopolymers occurs. So often industry wants to create a really wet batter so they can fractionate, like gluten, they can separate it, they can separate starch. So they isolate it and then use it in other products. And at this hydration, it's when you can get the maximal phase separation of the gluten phase, of the starch phase, blah, 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 blah. So this is likely the hydration at which a dough turns into a batter for wheat and spelt. This hydration, it's a rough range, but for any dry particulate matter, a flour, soil, whatever, above this hydration, when you add a solvent to it, the particles they act independently of one another, but below that hydration, they begin to collide with one another. And so when the aqueous phase emerges, the aqueous phase continues to grow up until this hydration point. And above this phase, the dough just becomes the aqueous phase because it dilutes all the other ingredients. The way we mix can change phase separation parameters. So on your left, so these are two doughs. They're identical. And they're half potato flour, half wheat. And this one, so the darker the color, and this corresponds to where the water is distributed. All the ingredients in this were mixed in, the dough is proofed and then baked, and minimal volume. And the one on your right, they took the potato flour on its own, the wheat on its own, they mixed the remaining dry ingredients between the two, and they divided the water into two, mixed doughs, and mixed it together. Oh shit, what happens? So that means that the way they mix changed the phase separation parameters of the dough. And you can determine where the biopolymers go and where the water goes. And you get this huge difference in volume. So I'll leave you these thoughts. Chlorination of cake flour changes gluten aggregation. It solubilizes the gliadins, and it causes gelation of the pentosands. So it means that they interact differently, those two biopolymers. And you don't get a continuous gluten network, so when you mix a cake, it's not fucking tough. The next one is when you add bran to wheat flour, like moving up an extraction from a T55 to a whole grain or whatever, a T80. It will change the phase separation characteristics. And so an extreme example is going from white flour to whole wheat flour, or even more extreme, something more pentosands, going to rye flour. And this explains why rye cannot form a continuous gluten network. It has nothing to do with like the bran cutting the gluten strands as traditionally taught. It has to do with the fact that you're changing the phase separation characteristics, how and where things go, because they want to avoid each other. And on the left is gluten that's been extracted from wheat flour. This one was extracted in water, and this one was extracted in a 90% ethanol mixture. Here, the solvent made the gluten want to shrink away and form into a tight ball to avoid the solute with the solvent because it's not interacting with the solvent. The other one, it interacts with the solvent, so it stretches out, wanting to combine with it. So a lot of this might be, what the fuck, but it's going to be online. I just want you to understand that where and how water goes and in what amounts is tunable or changeable. It's not predictable. Like, we can't predict it ahead of time because there's too many complex things that can go on. But it's not, dough is not a homogeneous environment. It's not everything equally distributed. It's a water and water emulsion with dispersed phases, and it's the way dough is structured. And and it really impacts the way it ferments, the way it mixes, the volume that you get, and it applies to everything. Like even beer is phase separated, coffee is phase separated. It's water and water emulsion. And whatever forms the continuous phase really determines the properties of its texture, its nutrition, its flavor, and it has deep implications. If I had more time, I'd go over the way that, whatever. But I'm going to open it up to some questions if you guys have any. Thank you. I mean, I really hope that I tried to make this clear, and if you don't understand it, it will be online and I'll upload this. But I think, I saw some nodding, I saw some people getting tired, which is okay, it's early in the morning, I get it. But does anyone have questions? Go, just shout out.
I would love to know how you've applied some of this to your own, like, practical baking.
Again, like, it's not about application, it's about understanding the way it's structured. So, I mean, like, it relates to microbial growth. I mean, like, if you can change the viscosity of the dispersed aqueous phase, you know, you're going to change the enzyme kinetics, you're going to change the rate of whatever. Bossonage is an example of using phase separation. I just want people to understand the way things are structured. So when it's usually thought that when we mix something, it results in a mutual dilution of all the ingredients, but it doesn't. You form these separate phases that differ in biopolymer concentration and differing in hydration. So when you measure water activity of something, that's a global whatever, but depending on where the microbes grow, that's what matters, the water activity of that phase where they are. So there have been instances where people use water activity to measure things like a mayonnaise that became shelf stable, and it showed the right water activity, but they weren't measuring the dispersed phase. And a huge outbreak happened, and it killed a lot of people. It has huge consequences, and I just want people to begin thinking about the way things are structured. So it's not so much about this has nothing to do with what you're going to go mix. I mean, can I do things? Yes. I've used a lot of this to be able to build awesome gluten-free bread. And
That's my question.
Yep.
How have you personally?
Yeah. So.
Things that you want to play around with?
Sure. I mean, like, batters, it's enabled me to think about if you want to take something and make it perform in a way that it doesn't normally perform. You can begin to understand the principles of what happens in a wheat dough, meaning that you have to find some type of insoluble protein, and then you want to make it at a concentration at which phase separation occurs. You want to find an insoluble protein that forms a network, and you want to try to have the same amount of it, and you can make little diagrams and whatever, and you get awesome gluten-free bread. I mean, that's a practical application. Other questions? Yeah.
Firstly, you didn't really understand my actual starter process.
Yep.
Hugely, but I found one of the things I was going to ask you understand. Have you come across trehalose?
Huh?
That's what I was talking about.
Oh, trehalose, yeah.
And the ability for it to control moisture migration.
Yep.
Do you have thoughts on it? Like,
Wait, I mean, does it? Yes.
does it?
Yeah, so different, so all sugars are what are called, what?
Tell us what that is. Like,
Trehalose is a type of sugar.
okay.
It's a type of polysaccharide. And whenever you add a sugar to water, they all dissolve in water. And sugars are what are called polyhydroxyl compounds. And things that are capable of forming hydrogen bonds are hydroxyl groups on molecules. And different sugars have different molecular shapes. And depending on the number of hydroxyl groups, it determines their ability to interact positively with water. And certain sugars have more hydroxyl groups that are free. Trehalose, for instance, has more than sucrose. So it's not that it's going to bind, but it's going to be the net attractive interaction that occurs depending upon the system. So different sugars change also the solvent characteristics.
So like you're using it to, like in frozen products, to reduce...
Oh, that's different.
Releasing the actual...
No, so trehalose, no, so this is unrelated. So what you're talking about, trehalose is used as a sugar by manufacturers for yeasted products and sometimes whatever, because it's a compatible solute that microorganisms import into their cell interior. They import several different what are called compatible solutes that enables them to deal with freeze-thaw stress. So cells in the cytoplasm are primarily water, and water moves about, and all biochemical reactions take place in water. And if water is present and there's something that can interact, then it's going to cause a biochemical reaction. That means metabolism is going to occur, and that means life. And that means that things can degrade or enzymatic reactions can occur. Because even when you freeze it, biochemical reactions don't stop. They stop at a much lower temperature. It just happens more slowly. So what happens is if a cell wants to survive being frozen, it exports water and imports other things to act as a solvent within the cell. Trehalose is one of those. There are a few others like glycerol. So it expels the water, and then it uses, and then the biopolymers that are inside the cell, they need to interact with something. So it imports trehalose or glycerol, and that replaces the water to bind the sites on the biopolymer that would normally be reactive, so that they become non-reactive. Yeah, exactly. Yeah. Because they're not reactive because of the sites on the biopolymer that would normally cause reactions to occur are being locked away by something else that is acting as the solvent, if that makes sense. Other questions?
And I think we might have to wrap it up unless there's one very quick question.
Go, Toph. No, go. No, go. Okay. Yeah, I know. Mariasha. Anyway, thank you guys.